Alright, let's get started. Hello everyone, this is SeungryongKim. So today we will finish Square Factorization and we'll move to the least square solution. So, okay, let's review the Square Factorization. So, this is a Square Factorization. This is the Theorem 12. If A is an n by n matrix with a linear independent columns, then A can be factorized as A is equals to Q and R. Q is an n by n matrix whose columns form a also normal basis for the column space matrix A, and R is an n by n upper triangle inverter matrix with positive boundary on each diagonal. Looks like this. So first of all, so to become a linearly independent column, and M should be larger than n. If n is larger than, greater than m, it's not possible to make a linear independent column. So this is first. This is one of the constraints. Thank you for Jung, right? So anyway, so for the n by n matrix with a linear independent column, A can be factorized Q and R. So first of all, how to construct the matrix Q, which is also normal matrix, so also normal basis, so we can do by the Gram-Schmidt process from the matrix, the column vectors of matrix A from here, and then we have to construct the matrix R, because the span of the x1 and x2 and xk is equal to span of u1 and u2 and uk. So there we know there exists a constant R1k, R2k, RKk, such that xk is equal to R1k times u1 plus RKk times uk plus 0 times uk plus 1 over 0 times uk un. So this make this kind of vector Rk is equal to R1k, RKk 0, 0, 0 transpose. So we will have this kind of Rk vector which can fill the R matrix R. So it looks like this. So today we will see the examples of this Square Factorization. Find the Square Factorization of matrix A 1 1 1 1 0 1 1 1 0 0 1 1. So first of all, let matrix A consisting of the three column vector x1, x2, and x3. To find the also normal vector, or also normal vectors, also normal basis, we first obtain v1 is equal to x1 from the Gram-Schmidt process. Gram-Schmidt process, 그렇죠? Gram-Schmidt process. Then, and its normalized vector is u1, which is the normalized from the v1. So to find the matrix R, I mean the each vector. So first of all, u1 is normalized from the v1 by the length of the matrix v1. So which is going to be the v1, length of the v1 times u1. u1. So we already know v1 is equal to x1 by definition. So x1 is equal to v1, length of the v1 times u1. So from the here, the length of this vector is 2, 그렇죠? Length of vector is 2. So which gives us R11 as 2. So that is our matrix R1 is 2, 0, 0. 2, 0, 0. 2, 0, 0. Because x1 is equal to 2 times u1, 0 times u2 plus 0 times u3. So R1 is the 2, 0, 0. Next, we want to we obtain the V1, the next vector, by Gram-Schmidt process. V2 is going to be the x2 minus fraction x2, also a fraction of x2 onto the W1, which was defined, looks like this from the Gram-Schmidt process. 그쵸? So x2 was here. 그쵸? 0, 1, 1, 1. 그쵸? Then this one is going to be 3 over 2. We already discussed this one in the previous example. This is exactly the same vectors, right? So you can easily compute this one as a 3 over 2, and u1 was the 1 over 2, 1 over 2, 1 over 2, 1 over 2. 그쵸? Then it's going to be looks like this. This is the V1, V2. Then, right? Then its normalized vector u2 can be just normalized of the by normalizing the V2 such that V2 over length of the V2. Then it's going to be looks like this. You can easily do that, right? So from here we want to represent vector x2 in terms of the u1 and u2. How? From the this one, 그쵸? This one and this one, we can represent x2 as a v2 plus x2 in a product to u1 in a product to u1 times u1. We already know v2 from this one. v2 equals to the length of the v2 times u2 plus x2 in a product to u1 in a product to u1 and u1, right? Then we already compute this one and this one, which is equal to 3 over 2. Which one is equal to 3 over square root of 12? Square root of 12. So our this is R2. R2, the second column in matrix R, it's going to be the 3 over 2 from here, 3 over square root of 2 and 0. This is R2, right? Similarly, for finding V3 is equal to x3 minus fraction of the x3 onto the W2, substrate W2, which is equal to x3 minus x3 over x3 in a product to u1 over x1 over x1 in a product to x1 times x1 minus x3 in a product to u2 over x2 in a product to u2 times y2. So we already know this one. So this is a operation of the x3 over onto x W2. So this is just to be the looks like this. 그쵸? This is x1, x3. This is the 3 over 2 x u1. This one it's going to be the maybe 1, and this is the u2. 그쵸? u2. Then it's going to be looks like this. So this is the vector v3. Then each normalized vector u3 it's going to be v3 over length of the v3. Then it's become looks like this. So similar from the here, in this case x3 it's going to be the u1 plus 2 over square root 12 u2 plus 2 over square root of 6 u3. Then r3, vector r3, column vector r3 is going to be 1 from here, 2 over square root of 2 12 and 2 over square root of 6. This is r3. So from here we already compute the q as a u1, u2 and u3, which was looks like this. Then matrix R consisting of the vector r1, r2 and r3, which was defined 200 here and here. This is a QI factorization from the original matrix, this one. this is QR factorization. It's very useful factorization. Next chapter we will talk about how to use this kind of factorization. But as you can see, this example form, finding matrix R is a little bit complicated, right? Because we have to consider this one and this one and this one, right? Fortunately, we have a very simple way to find out QR factorization. So this is last slide. In the last slide, we will see the very efficient way to find a matrix Q and R, a matrix R. So, alternatively, if Q was already computed by the Gram-Schmidt process, 그쵸? Instead of comparing matrix vector R here and here and here, it's very complicating. 그쵸? Instead of this, one can compute R and Q transpose A is equal to Q transpose QR, which is the I times R and R. Why? Because the Q transpose Q is equal to identity matrix. Why? So, okay. We want to find out matrix R that satisfy A is equal to QR by comparing, by multiplying Q transpose left hand side and right hand side, looks like this. We achieve this matrix, but Q was also normal. Q consists of also normal columns. So from the previous theorem, it should be identity matrix. So this is just the identity matrix. Then R is going to be the Q transpose A. In other words, we can easily compute the matrix R by Q transpose A because we already know A and we already compute the matrix Q by Gram-Schmidt process. Then we can just compute this matrix multiplication Q transpose A. We already know how to do this. First of all, this one coming from the first column from the here and first row here. First row from the first matrix, first row from the second matrix. So this is 2. For this one, we should compute this matrix times this one. Similarly, we can find out 2, -3 over 2, 1, 0, blah 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 blah. So this exactly. Sorry, there was a typo. It should be plus. Right. So this one exactly same to this one. So this is very efficient way to find out your matrix R. So this is the QR factorization. 그렇죠? Okay, that's it. So this is the end of chapter 6.4 So let's move to the lecture note 11, chapter 6.5. So in here, this is the least square problem, chapter 6.5. So today, here, we will talk about what is the least square solution and how to use QR factorization to solve this kind of matrix, this kind of problem. Alright, so previously, we already talked about QR factorization, least square solution. Where? From lecture 9 here, 그쵸? We already talked about the best approximation theorem. Where was that? Here. We already talked about best approximation theorem, 그쵸? Here. Best approximation theorem was the y hat, 그쵸? Where's y hat? 그쵸? Y hat is the closest point from the y to the subspace W, 그쵸? Then in Lecture11, in least square solution, we will generalize, we will present the systemic way to use the properties to solve your inconsistent system. And then we extend this problem solving skill by using the Square Factorization. Right. So, first of all, the least problem means inconsistent system x equals b, which does not have solution, 그렇죠? Which have no solution, arise often in many applications, so many applications. But you want to know, because we can't find the exact solution for this x equals b matrix equation, but we want to find out, maybe you want to find out approximate solution. When a solution is demanded and none exists from here, the best one we can do is to find an x that makes ax as close as possible to b. To find an x that makes ax as close as possible to b. But ax cannot be b, 그렇죠? But we want to find out ax close to the b. Then in this case, vector x can be the approximative solution. In other words, think of the ax as an approximation to b. Then, in this case, general least problem is to find the x, such kind of x that makes this one, length of b minus ax as small as possible. This is the least square problem. In this case, vector x that satisfies this constraint can be the approximated solution for the inconsistent system. Approximated solution for ax is equal to v. That's the topic of this section. Okay, let me start with the definition. But this definition is almost similar to our best approximation theorem in previous lectures. Matrix A is an n by n matrix and B is in Rm space. The least square solution of the A equals B is an x hat in Rm space such that length of the B minus ax hat is smaller or equals to length of the B minus ax for any vectors x in Rn space. This is similar to the best approximation theorem, 그쵸? Similar to here. Let's suppose that okay. So let me from here. So the most important aspect of the least square problem is no matter what x we select, the vector ax will necessarily be on column space of the matrix A. So we seek on matrix vector x that makes ax to the closest point in the column space A to the B. In other words, here, let me explain here. We have to solve the ax equals b, but to make this matrixification have solution, the matrix vector b should lies in column space of matrix A here, but B, in this case, B stays outside of this column space or subspace. Then we want to find the approximated solution ax hat, AX hat, which lies in the column space of matrix A, and the the length, distance, or from vector P to the AX should be minimized. So in this case, we call X hat as a least square solution. Least square solution. In this case, AX equals 0 case, P minus AX, length of P minus AX is the minimum compared to the length of P minus AX for the any vector X in column space. That's a least square solution. General least square problem. The solution of the general least square problem. So in other words, we have to find out this X hat. Right. So first of all, we already know this one. What's that? What is that? This is the also projection of B onto column space matrix A. So what we want to do, we want to use this property to find out X hat. Let P hat as a fraction, orthogonal fraction of the P onto column space of matrix A. Here, 그쵸? Let's say P hat A times AX hat. Because the P hat is in column space of matrix A, the equation AX equals to P hat, this one, is consistent because the P hat in column space of matrix A, and there is an X hat in Rn space such that AX hat is equal to P hat. 그쵸? In addition, since the B hat is a closest point in column space of matrix A to the B hat, vector B, vector X hat is a least square solution of the A equals B if and only if X hat satisfies 1. This is very, very intuitive. We already talked about this one, but this is the same meaning of the previous lectures. First of all, column space can be represented by column vectors A1, A2, AN. 그쵸? Then we can find out P hat by the orthogonal projection definition. 그쵸? In other words, by the orthogonal decomposition theorem, the projection P hat has a property that P minus B hat is orthogonal to column space, so P minus A hat, X hat is orthogonal to each column of matrix A. 그쵸? From here, this definition. So P minus AX hat, this vector, should be orthogonal to the each column vectors A that span this column space. In other words, if AJ is any columns in matrix A, then AJ inner product of the P minus A hat, 그쵸? P minus A hat should be 0 because they are also on each other. So AJ hat transpose times P minus AX hat should be 0. In other words, in addition, since each AJ transpose is the row of A transpose, it means that A transpose become a A1 transpose A2 transpose A and transpose from this one by considering the or AJ, AJ1, AJ2, and AJN, this one can be represented by matrix multiplication A transpose times P minus A X hat, which is equal to 0, matrix. By the definition of the matrix and vector multiplication, A transpose B minus A transpose AX hat is equal to 0 from here. In other words, A transpose A X hat is equal to A transpose B. Right? This calculation shows that each least square solution of the AX equals B satisfy the following equation such that A transpose AX hat is equal to A transpose X. The matrix equation, this matrix equation represents the system of equation called normal equation for the AX equals B. In other words, the solution of this is often denoted by X hat. Because now this one can have the solution of the X hat, which is equal to, which will be the approximate solution for the AX equals B. That's the normal equation for the AX equals B. Let me summarize so far. Let me summarize the concept so far in Korean하게. 자, 여러분 알겠죠? 그래서 무슨 얘기하고 있는 거냐? 사실 이 리스큐어 솔루션은 리스큐어 프로블럼 or 리스큐어 솔루션은 우리가 벌써 얘기를 했어요. 다 앞에서. 뭐 하는 거냐면은 AX equals B가 어떤 솔루션 없는 경우에, 사실 대부분의 경우는 여러분들 솔루션이 없어요. 여러분들 시스템은. 근데 그럼에도 우리는 AX equals B의 어떤 솔루션, 어프로키시메이티 솔루션을 찾고 싶은 경우가 많아요. 그쵸? 그런 게 뭐냐? 어떤 경우가 어프로키시메이션 솔루션이냐? 어떤 X가 뭔지 모르겠지만 AX가 B랑 같을 수는 없겠지만 B와의 차이가 가장 작아지는 X가 무엇이냐가 어프로키시메이션 솔루션이고요. 결국 이걸 찾는 걸 얘기를 하는 거였고, 결국에 이거는 베스트 어프로키시메이션 세어럼과 유사한데, 결국 랭스 B-AX 이 B-AX보다 어떤 X로 했을 때보다 더 작아지는 경우에 그 X를 찾는 거라고 바뀌는 거고, 그게 언제였냐면 그려보면 AX 이 결국에 올소관 프랙션인 경우에, 왜냐면은 얘가 이제 컬럼 스페이스 안에 있어야 되니까, 매트릭스 A의 컬럼 스페이스 안에 있어야 되니까 B가 밖에 있으니 1로 프랙션 시켰을 때 가장 가까운 점 올소관 프랙션에 있어야 되는 거고, 결국엔 쭉쭉 계산해보면 돼요. 그쵸? 그렇기 때문에 쭉쭉쭉 B가 컬럼 스페이스에 올소관 프랙션이어야 되고, 쭉쭉쭉 계산해보니 그런 프로퍼티 때문에 B-AX가 each column matrix A와 올소관을 해야 된다라는 프로퍼티 때문에 쭉식을 써보면 이렇게 되던 거예요. 그래서 이걸 어떤 매트릭스 폼으로 바꿔보니 A 트랜스포즈의 B-AX equals 0를 푸는 게 됐고, 이걸 쭉 정리를 해보니 이런 매트릭스 식이 나온 거죠. 매트릭스 이퀘이션 식이. 즉 이게 이제는 노멀 이퀘이션이다 라고 부르는 거예요. 너무너무나 중요한 얘기고, 이 노멀 이퀘이션 결국에 여러분들 어떤 AX equals B는 이제는 솔루션 없는 경우에 이렇게 노멀 이퀘이션을 만들어서 이걸 푸는 걸로 바뀌어버리는 거예요. 왜냐? 이 노멀 이퀘이션은 솔루션이 존재하기 때문에. 언제? AX hat으로. 그 X hat이 뭐냐? AX equals B의 가장 approximate 솔루션이기 때문인 거죠. 그렇죠? 그게 이제 바로 노멀 이퀘이션이다 라고 하는 거예요. 그렇죠? 너무너무나 중요한 얘기고, 너무너무나 중요한 이퀘이션이에요. 알겠죠? Right. Okay. So, in other words, in Theorem 13, the set of least solution of the AX equals B coincide with, 그러니까 least solution은 coincide with non-empty set of the solution of the normal equation A transpose AX equals to A transpose B. This is the normal equation. 오케이? 알겠죠? Okay, I think that's enough. I think we have to finish here. So next week we will see some examples of the solution of the generally square solution and we will move to the next topic. Okay? 그 우리가 이제 이번 주 축제 기간도 있고 해서 여러분들 라이브 미팅 말고 라이브 렉처 말고 이렇게 레코드 비디오로 준비 해 봤어요. 그래서 여러분들은 축제 마지막까지 잘 즐기시고 좀 시간 남을 때 이 강의도 듣고요. 우리는 다음 주에 또 보도록 합시다. 알겠죠? Okay, so this is end of today's lecture and this week's lectures. Thank you very much and see you next week. 여러분 고생 많으셨고요. 우리는 다음 주에 보겠습니다. 알겠죠?